So let's begin like we always do with physics. So all computation is physical, right? I mean, bits take up space, they require time to change, they require energy to change. So all of that means that bits are physical things. On the right there you see a scanning electron microscope colorized image of a bit, in this case 12 iron atoms. So there's a thing called Landauer's principle, and it says that the minimum free usable energy necessary to erase a bit is given by that expression, k times t times the log of 2. Now, k is the Boltzmann constant, and t is the temperature, and that's an interesting little relationship, and there's some debate about it, but it's survived experimental validation. It applies to quantum computing as well, and even though this was proposed in 1961, it took a long time to sort of work its way through the process, and it turns out that this has been shown now to be derivable from the second law of thermodynamics. And that's a good guess as to why that is that there's a log in there. So you can also look at Moore's law, Kuhne's law, Dennard's scaling, reversible computing, and so on. But basically, everything you do on a computer has a physicality to it. So for example, here's some side channel information. A side channel is a channel on which you might think of information being inadvertently sent. So normally we send bits over a wire, and that's the primary channel. But we might also send some electromagnetic fields out into the world as we do that, and those are secondary or side channels. So up at the top you see a power trace, and what's going on there? Well, you'll see first AES round, second AES round. So we're computing something. In this case, we're doing cryptography, and here you can even see the parts of the AES algorithm taking place. And if you can very carefully monitor this stuff. And if you want to go read this paper to see more of the details, you can use side channels to do things like reveal secret keys being used for encryption without looking at anything the program's doing, just looking at the side effects of the computation. So let's take a look at memory real quickly. So down at the bottom we have dynamic RAM, so refreshed memory. The usual thing you think of when you put memory in your computer. It takes a long time to talk to that, so we put some stuff in a cache, and that's the L3 cache. Typically it's shared among all the cores on a particular die. And then each core has its own L2 cache, each one has its own L1 cache, and then you have the CPU itself, which can have some internal caches as well. So when CPU wants something, it looks for it in its L1 cache. If it's a miss, it looks for it in its L2 cache. If it's a miss, it looks for it in the L3 cache. If that misses, then eventually it tries to schedule time to read it from DRAM. And it has to schedule that. Remember, in this case, there are 4 CPUs, and some of those CPUs may need stuff from memory. Some of them may need stuff written to memory. And all of that has to get organized and marshaled so that we make efficient, productive use of the RAM. If we can avoid writing stuff out here or reading stuff from here, that is for the best. Here's a little image of one of these chips. In this case, there's 4 processors. You can see the L2 caches. You can see the DRAM interface over here on the side. You see the actual DRAM slice over here, and then you have the L3 cache. Dynamic random access memory was invented the same year as me, 1968. That's when it was patented. And the Intel 1103 was the first one. You can see a picture of it over there on the right. First commercially produced DRAM memory chip. It displaced the magnetic core memory that had been used up to then. And it stored 1 kilobit. I said bit. So that's 1024 bits. In other words, that RAM holds 128 bytes of memory, which should be enough for anybody. Now this worked well, except that it occasionally suffered something called bit line to cell coupling. Now that is, here's a little diagram of it, and you can see various things going on here. We have data in, write select, read select, and a data outline. and a few transistors along the way here, a capacitor that's being charged or discharged to hold the information, and there you go. And what could happen is the electrical field on the bit line could influence the field on the memory cell, and this caused a disturbance error. Here's a modern DRAM. We've come a long way, baby. So this holds more than 128 bytes, quite a bit more than 128 bytes. And here's a much simpler version of what's going on. This isn't exactly what's happening, but this is a nice simplified version that may be a little easier to understand. There's an address line. When that line is selected, then we're putting some voltage here. And here's a bit line. Let's say we're writing. When the bit line is selected, we're putting a little bit of voltage here. If there's voltage on the address line, that voltage can propagate over here and charge the capacitor. If we enable this and we sense what's on here, voltage on the capacitor can make its way over here and influence the bit line. But you'll notice what happens. When I read it, when I write it, I charge it up. But when I read it, I drain the charge off of here through the bit line. And so basically when I read it, I destroy it. So what I need to do is find a way to read it and then put the information back. So the next time I read it, it's still there. And that's what in fact happens. The read lines go to something called a sense amplifier, and so they're basically latched in so they can be sent back, and then they're written back before they are copied out. So, you know, even if I don't do that, over time, this little capacitor is going to lose some charge, right? It's going to lose charge this way, or it's going to lose charge this way. This charge is going to leak out. And think about these little chips. These capacitors are jammed in together. And it's going to gradually leak out with this charge. And so periodically, I need to refresh them all. I need to read them and then write them back. And I do that to an entire row at once, and that's why it's dynamic RAM, dynamically refreshed read-only memory. Now there's something called parasitic capacitance. So think about this. When you have two components and they're in a circuit and you begin to move them closer and closer and closer and closer, you can think about the field around each of the different elements. And eventually you can get close, you can get them together, and you end up with a non-zero capacitance. In reality, in theory, there's a non-zero capacitance between any two conductors. But you know that really matters when you begin to get them really close, and things are really close in a modern integrated circuit. Often you can ignore parasitic capacitance, but it can become a problem when you meet either one or both of these cases. Components are really close to one another. In that case, you start to have to worry about parasitic capacitance, or you're in a really high frequency application where you're trying to jam through changes really quickly, and the capacitance is maybe acting like a choke. So computer memory is subject to parasitic capacitance. In this case, nearby memory rows can become weakly coupled. And this is not a new or surprising result. The paper you see over on the right there is from 1990, and they talk about parasitic capacitance of multi-level interconnects in DRAM circuits. They're warning you about the possibility of parasitic capacitance in these circuits and discussing how that might happen. Is this useful? Well, I guess it depends upon what you're trying to do. Suppose that I have a bank of memory over here, a bunch of rows of memory. What I do now is I write to row 1, and then I write to row 3, and I write to row 1 and row 3 as fast as I possibly can. Okay, just constantly I'm changing these two rows in my dynamic RAM. And because they're changing so fast and I'm pumping current through the memory, I set some voltage in there to push some charge onto the capacitor. I drain it. I do that again. I keep doing that. That charge can leak over here into my target row, which is actually row 2. And it turns out I can get bit errors in row 2 if I do this. What about code to do it? Well, here's some code that does it. I read from EAX, I read from foo, read from bar, and then I flush the cache, and so I force it to write the back. CL flush is an unprivileged instruction. Maybe it shouldn't be. This flushes the cache line associated with these guys. And now I do this again, and I can just do this again and again and again until I generate a memory error. Can it be exploited? Sure it can be. So Seaborn describes how to do this. They did a couple attacks. For the first one, they used copies of the code itself. Memory errors self-modified the code, resulting in executing a syscall and escaping containment. For the kernel attack, they used shared memory with read-write protection and filled it up with page tables. How do you do that? Well, each process gets its own copy of the page table. So you spawn off lots of processes, and eventually you try to fill memory up with page tables. A memory error can cause one page table to have an error, and since it points to another page table, maybe you then end up with read and write permission to that particular page table. And so there you go. Now all this requires code running natively on a computer in a compiled language, unless there's a program on the machine that provides the features that you can use to exploit to have the same result. In general, it's hard. Memory controllers randomize their state, and the top bits of memory address are, in a sense, hashed. Okay, but it turns out this is more or less a solved problem. If you look at Pesci and Maurice, they've taken the time to try to figure some of this out. And in fact, the attacks seem to be getting not harder, but actually easier. So you need timing, physical address mapping, and ordering of events, and it turns out that a lot of different environments can begin to give you the pieces that you need. So here's a paper from, or a report of one from Dan Gooden, where they talk about flipping bits on an Android phone. That's nice. And if you want to know more about it, here's a paper from 2020's IEEE S&P on Rambly. Reading bits in memory without accessing them. This is an interesting paper. You may want to give that a read. NetHammer, inducing rowhammer faults through network requests. That's a thing, also in 2020. IEEE S&P in Europe. And I think NetHammer is especially interesting. We present NetHammer, a remote rowhammer attack without a single attacker-controlled line of code on the target system. Not even JavaScript. I think this is amazing. NetHammer works on commodity consumer-grade systems that either are protected with quality of service techniques or that use uncached memory, flush instructions, or non-temporal instructions while handling network requests. Sometimes the network card wants to talk directly to memory to do its work, and when that happens, maybe I can use the network card to achieve the same effect. So what? Some security critical code now employs randomization to prevent side channel attacks and to make attacks that might exploit regular timing more difficult. And we can go all the way back to 2011 to see some of that. And there's a tendency to try to move secrets out of memory quickly after they are used, because memory, maybe it's not that secure in a multi-process, multi-user environment. The point of all this is physical attacks can happen remotely, they can undercut security, and they can be enabled by the software on the machine. And what do we say about the software that may be enabling such an attack? Is it secure? Is it insecure? Would you know? You wouldn't necessarily know, right? You've written the software, someone comes along and finds this odd physical property and exploits it. There's homework due on the 6th. Head out to GitHub or GitLab, go find a project, find at least 3 potential threats, and submit your diagram of that project and the threats. Let's talk about a more systematic way of maybe doing threat analysis. So remember our questions. What are you building? what can go wrong, what should you do about the things that can go wrong, and have you done enough analysis? Right? We're doing threat modeling. Ad hoc threat modeling, if you've been doing the homework, ad hoc threat modeling probably seemed a bit ad hoc, and that's because it is right there in the name. Can we make threat modeling more systematic so we can do a better job, and I'm putting scare quotes around better, and can we perfect threat modeling? So let's consider the most common threats in a particular domain. And so top 10 threats from OWASP over here on the right: broken access control, cryptographic failures, injection, insecure design, so on. Well, this is what attackers do based on intelligence gathered by various stakeholders, right? We build these lists to say, here's what the attackers are doing. Here's what they're most commonly trying to go after, the most heavily exploited vulnerabilities and weaknesses. It's expert opinion based on whatever evidence is available. Is that perfect? Of course not, right? We don't know the unknowns that we don't know, so who knows? The advantage is it can be customized to your particular domain, and it deals with active, serious threats. The disadvantage is sometimes things fall off the bottom of the list. That doesn't mean they're not a threat anymore. It just means that, like the 11th threat, then, you know, how far down the list do you want to read? Here are the top 25 weaknesses as per MITRE. We saw this last time. Some of these are obviously bad, like hard-coded credentials, but you'll notice it's not in the top 10. Right? Null pointer dereference, they didn't quite make it into the top 10. So wherever you decide to cut your list off, you're probably dropping a whole bunch of really important stuff off the other end of it. Can we, instead of considering each one of these, maybe we consider broad classes of threats or categories? And then we try to organize and marshal our ideas around addressing each one of those categories. Sure, that would be something like Stride. So Stride comes out of Microsoft, and Microsoft has had its security struggles over the years, and so they needed a way to do this in a systematic manner. And they looked at 6 things: spoofing, tampering, repudiation, information disclosure, denial of service, and escalation of privileges. Those are the 6 things. And so you can consider each one of these and ask, does this apply to my project? And if it does, how does it apply? Spoofing identity, pretending to be someone or something other than yourself. That one's obvious. Tampering with data, you could modify something on a disk, on the network, in memory. You might go look in the temp file system, try to find some temporary files, and if they are readable, they might leak information. If they're writable, you might be able to tamper with a process, an active process on the machine. Repudiation, that's claiming you didn't do something you did, or were not responsible for something. Information disclosure is just what it said, giving out too much information. Denial of service and elevation of privilege, again, just what they say they are. The advantage to Stride is you get better coverage because now you have to think about things like repudiation, which you might not have been thinking about before, or about denial of service. And this encourages you to begin to think like an attacker, right? I have my system maintains logs. Can someone do something and then tamper with the logs to say that they didn't do it, right? That's repudiation. And now I start to think about these various things. The disadvantage is it's still very high, and so it becomes ad hoc within each category. But now there are at least categories. So, what are you defending? Who are you defending it against? What are some tactics they might use? What are some techniques that can be used to accomplish their goals? And how do you defend yourself against these techniques? Right? You start to try to think like an attacker. And when you think that way, you might end up with something like MITRE's Adversarial Tactics, Techniques, and Common Knowledge, or ATT&CK. So the MITRE ATT&CK framework, again, MITRE owns this space, is a fairly comprehensive, detailed list of the way in which attackers launch their attacks. An advantage is comprehensive and detailed. Disadvantage, maybe too comprehensive and detailed to use to inform you as you're writing your code. Let's take a look at it though. So here is the MITRE ATT&CK framework. If you head to attack.mitre.org, you'll land on this page. And here's the framework. At least this is the matrix for enterprises. And I've got it set up here, and you can see there's reconnaissance, resource development, persistence, credential access, collection, and all of this stuff on here. And some of these, you'll notice, are just little sections like browser extensions or compromised client software. Some of them have this little thing here, and when you click on them, when you arrive here, you'll see procedure examples and all of this stuff. But you go back, if you click out here, it expands, and you can see that here, create or modify system process, launch an agent, system D interface, Windows service, launch daemon, let you expand them. Forge web credentials, there you go. And so this is a pretty comprehensive system. All these things are links, so like credential access takes you here, gives you some details, and shows you all the little stuff that was on there. Other side, adversary in the middle, brute force, adversary in the middle, brute force. So just different ways to explore it. And we can, drop down to the bottom, and you can see examples, and you can see mitigations, and then ways to detect it. And then there's other stuff on here as well. So it's very comprehensive. There's a lot of information here, and people use this, right? They sort of go through this, and they'll highlight the sections that are relevant, and then they can work on each one of those. So this is something that does in fact get used. This homework is due on the 6th, we talked about earlier. And now what I'd like you to do is to revise your threat analysis using the STRIDE approach, and indicate to me any new threats that you find when you do this.